Hello, this is Héctor, your AFM expert at Nanosurf. You might remember that a few weeks ago we looked at the surface of my mobile phone with one of our industrial solution AFMs. We basically put it there and do some measurements on top. This week I want to look inside of the phone. That's why I took a mobile phone, I broke it into pieces. From the pieces I took the CPU and using a focus ion beam I cut the CPU. Then I mounted the CPU vertically in a holder, and using the AFM probe in conductive mode, I look at the cross-section of the chip. And from the conductivity measurements, we are able to identify different elements. If you follow me into the lab, I'll show you how I did it. The first step is to open the mobile phone, basically breaking it apart and extracting the CPU. To do so, we use a heat gun and basically melt away the solder. The CPU is a Samsung Exynos 8895 with 10 nanometers technology nodes. In order to expose the integrated circuit, we need to decap it. And in this case, we use a combination of acids and clean the acids, wait, and repeat. The CPU is formed by 3 different chips stacked together, so we need to separate them and break the wire bonding between them. The next step is to cut the chip in half, and for that we use focus ion beam. The ion beam has a double purpose. First we use it for cutting, and then we use it for polishing the exposed edge. And the idea is that we will use the AFM in conductive mode to look at the edge and try to see the transistors over there. Here on the SEM images, you can see that the focus ion beam expose the internal parts of the chip, and we can see them on the edge. It's also possible to see that some areas are flatter than others, so we will try to go for the flatter areas with the AFM. In order to mount the sample, we use silver paste and a metal disc. The silver paste holds the chip vertically, so with the AFM we'll be able to access the edge, and at the same time is conductive, so we will use it for closing the electrical circuit between the AFM probe, the chip and the ground. Here you can see the chip mounted on the AFM, and the electrical connection is done through the SSRM holder. You can see that I took the precaution of leaving enough space, so when I lower the scan head, it's still far away from the edge. And landing on this surface is quite easy. So you use the optical microscope and the motorized stage to align the edge with the probe. I choose this configuration perpendicular because I think it will be more symmetric in terms of electrical coupling, because if I go along the chip, sometimes part of the cantilever might be on top of the chip, sometimes it might be mid-air. In this case, most of the cantilever is in air. You can do the landing in dynamic mode or static mode. Since we will be measuring conductivity, probably the best thing is to go with a static, and then you make sure the parameters are already the right ones for starting the imaging. Next is to capture the images, and to do so we will use something called SSRM, Scanning Spreading Resistance Measurements. is a technique where you image the topography in a static mode, and at the same time you measure the electrical current between the tip and the sample, and you use a logarithmic amplifier to measure the current. The idea here is that if a tip goes through a conductive area, and this area is connected to the ground, you will have an electrical current flowing, which is proportional to the resistivity of this part. If you have a conductive area but is not grounded, it's not connected to ground, you will see zero. Or if you have a conductive area and is the tip cannot touch it because it's inside of the material and is not connected to ground, you will see also zero. Why having a logarithmic amplifier? Well, in these samples, it's very typical to have resistances that vary several orders of magnitude from one area to another. So if you have a linear amplifier, you will see basically bright and dark spots only. But with a logarithmic amplifier, you are able to see everything in between. So this is good when you have areas that have different levels of doping and those different levels of intermediate levels of resistivity. And with this, we come to the results. Here you can see, first the SEM image again, just to remind you that where we are in the cross section. Then topography, AFM topography on the left, and conductivity in a logarithmic scale on the right. As you can see, there is many spots. In this case, bright means more conductive. There is big electrodes, there is tiny structures, and there is many things we initially don't recognize. However, if we keep zooming in, we see that there are these tiny periodic structures, and this is very likely to correspond to field effect transistors. Because according to the documentation of this chip, this is the type of transistors that are in this CPU. The size or one of the relevant dimensions is around 10 nanometers, and this is what we see between these small fingers. And although it's not possible to confirm this, it's very likely that these are the field effect, the field effect transistors, which is something very cool, thinking that we can see this with SSRM. And this is it for this week. Let's have a little recap. We took a mobile phone, we opened it in order to expose the elements inside of it, and then we extracted the integrated circuits, basically the CPU. The CPU is packaged, which means that we have to decap it in order to access the silicon elements inside. In our case, we use a chemical process for the decapping, and because this process uses several types of acids, if you want to reproduce it, please seek the assistance of an expert, and always do it in a controlled environment. Don't try it at home. After decapping the chips, we took it into the focus ion beam machine, and we cut the chip, and on the exposed edge we polish it with the focus ion beam in order to have a very flat surface for AFM. With the chip cut in this way, we mount it in a metal disc and we put it in the AFM. The AFM, we use it to look at the edge of the structure of the sample, and then we use spreading resistance to look at the conductivity changes. The scanning and spreading resistance measurements uses a logarithmic amplifier. Why a logarithmic amplifier? Why this is important? It's important because in this type of samples you have parts that are insulating and you have parts that are extremely high conductive. They have extremely high conductivity. And you have everything in between, depending on the doping level. And in order to see all of this, which spans through several decades of resistance, you need to have a logarithmic element in your circuit. This is how it helps. Looking at the data and looking at some internet bibliography, it seems that we managed to observe elements belonging to the FinFET technology, because we see elements with different level of doping, different level of conductivity, and we see that some of the features agree with the 10 nanometers technology that it's part of the documentation or is mentioned in the documentation of this integrated circuit. So it was really cool. I hope you like it. If you have any comments or suggestions, please leave it in the comments. And otherwise, see you next week.